Hello and welcome. In this explainer, we're going to do something a little different. We are going to take one single, pretty tricky exam question and completely deconstruct it piece by piece so you know exactly how to nail it for full marks. And our subject today, a GCSE Physics question all about the dynamo.
Now, this isn't just some random question I made up. Nope. This is question 9 from the actual 2023 AQA GCSE Higher Tier Physics Paper 2. It's a 6-marker and it's broken down into 3 parts. And here's the best bit. We are going to use the official AQA mark scheme to build our perfect answer. This is the inside track, you know? This is how you make sure you get every single one of those marks.
Right, let's get started. The first part of the question, 9.1, is all about the fundamental principle of how a dynamo even works in the first place, how it induces a current. So here is the exact wording. The coil is rotated. Explain why a direct current is induced in the coil. Now, pay close attention to the key phrases here. Explain why and direct current. It's a 2-mark question, which is a big clue that we're looking for 2 separate, really important points to make.
Okay, so what does the perfect answer look like according to the people who be marking your paper? Well, to get that first mark, you have to use the magic words. The rotating coil cuts magnetic field lines. That specific phrase is absolutely key. That action is what induces a potential difference or a voltage. Then, for that second crucial mark, you've got to explain the direct current part. And the secret ingredient for that, it's the split ring commutator. You have to mention it. It's this clever little device that reverses the connection every half turn, which makes sure the current out in the circuit is always flowing in the same direction. And just like that, you've got your 2 marks. Easy, right?
Moving on to part 9.2. This next bit is all about testing whether you can take that idea we just talked about and turn it into a picture. It's a visual test of your understanding.
The question asks you to sketch a graph of the potential difference for 2 full rotations. Now, this is only a 1-mark question, but trust me, it is a super easy mark to lose if you're not precise. It's all about showing that you really understand what the output from this specific DC dynamo looks like.
So before we even look at the perfect sketch, let's just think it through logically. We know from the first part that the split ring commutator is creating a direct current. So what does that mean for a graph of potential difference? Well, it means the voltage is going to rise and fall, but, and this is the key, it will never go negative. It's always going to be on the positive side of that axis.
And there it is. The perfect graph is a series of positive humps. Each little hump represents 1/2 turn of the coil, where the potential difference goes from 0 up to a maximum and back down to 0. And look, it is always positive. It never dips below the axis. Since the question asks for 2 revolutions, you need to draw 4 of these humps. This shape, by the way, is what we call a rectified wave. To rectify something just means turning an alternating current, which goes both positive and negative, into a direct current that only flows one way.
All right, let's tackle the final part of the question, 9.3. This is the big one, the 3-marker, and it brings in a really, really important concept, the conservation of energy. But it's kind of disguised as a question about forces. So here's the scenario. You disconnect the lamp, and all of a sudden, the dynamo is way easier to spin. The question is why? What's going on? This is one of those questions where you have to connect a few different physics ideas together in a perfect logical chain.
Okay, so the whole secret here is understanding this chain reaction. Let's walk through it. First, when the lamp is connected, you've got a complete circuit, right? So a current flows. Second, we know that any current flowing through a wire creates its own magnetic field around it. Third, and this is the real kicker, this new magnetic field from the current interacts with the field from the permanent magnet, and it creates a force that opposes the original turning motion. It's an amazing bit of physics called Lenz's law, which basically says that any induced current will always try to fight the change that created it. You're literally fighting against the electricity you're generating. So when you disconnect the lamp, you break the circuit. No circuit means no current means no new magnetic field, and therefore no opposing force. It suddenly becomes a breeze to turn.
So let's just pull back for a second and look at the big picture here. What was the examiner really trying to test with this single 6-mark question?
You know, this summary table really shows you how cleverly this question was designed. Part 9.1 was all about your core knowledge of electromagnetic induction. Part 9.2 was about visualizing that DC output, drawing that rectified wave. And Part 9.3 was the real deep dive, testing your understanding of energy conservation, how generating that current actually requires you to do work against an opposing force. You can see how they're all beautifully connected.
So there you have it, a full breakdown of a 6-mark Dynamo question, using the perfect answers straight from the mark scheme. And that just leaves us with one final thought. Looking back at those 3 parts, be honest, which one would have given you the most trouble under exam pressure? Was it the fundamental theory, the graph sketch, or that tricky energy conservation puzzle? Thinking about that is probably one of the best ways to focus your revision. Thanks for joining me on this explainer.